Hello, everyone. Today, I will talk about simple pair algorithms for single-site dynamics. It is a joint work with Yitong. Sampling from high-dimensional distributions is a fundamental problem in computer science. The problem can be stated as follows. Let mu be a distribution over Q power V, where V is a set on n sides, and Q is a set of Q spins. We need to sample a configuration X from distribution mu. The problem is among the earliest computer programs historically, and now it is a fundamental problem in data science. The Monte Carlo Markov chain method is one of the main methods for sampling. A canonical Markov chain for sampling from mu is known as Glauber dynamics. In a step of Glauber dynamics, from configuration sigma, pick V uniformly at random. Redraw the color of V according to the marginal distribution on V. It is well known that the chain is stationary at mu. If distribution mu is defined by local constraints, the problem can be represented as graphic model G. G contains all the n sides as vertices, where the distribution mu holds the conditional independence that for each side V, the marginal distribution on V only depend on V's neighbors. Then for Glauber dynamics on graphic model, when redrawing the color at V, it only depends on the configuration of V's neighbors. Glauber dynamics falls into a general framework of the single-site dynamics. For single-site dynamics, given a graphic model G and a local update distributions P, that for each site V and any configuration over V's inclusive neighbors, P defines a distribution over Q. In a step of single-site dynamics, we pick V uniformly at random, redraw its color according to the local update distributions. Except from Glauber dynamics, another well-studied Markov chain, known as Metropolis chain, is also a class of single-site dynamics. In the following talk, we only consider the Glauber dynamic, while all the algorithm, theorems, and analysis can be extended from Glauber dynamics to any single-site dynamics. The above Glauber dynamics is a sequential process. It raises a problem that whether we can convert into a parallel process. That is, can we execute some steps of the Glauber dynamics chain simultaneously on different processors? In a similar work, Mumuli, Vazirani, and Vazirani asked whether approximate counting for permanent is in RNC, while Tan answered it negatively, pointed out that the Jerome-Sinclair and the Borders chains cannot be fully parallelized. In the past decade, increasing attention has drawn to parallel sampling and inference motivated by big data science. The sequential Glauber dynamics actually comes from a continuous time version proposed by Glauber in 1963. In the continuous time process, each vertex holds its independent rate 1 Poisson clock. Then time from 0 to t, whenever a clock at node V rings, update V's color according to the marginal distribution on V. The continuous time and discrete time process are equivalent up to a speed up factor n. Now, our goal is to simulate time t continuous time chain in OT rounds in parallel. The main challenge is that when simulating adjacent updates within a round, it may cause concurrency issues. We give a simple parallel algorithm that can faithfully simulate Glauber dynamics. Here is our main theorem. As long as a Glauber dynamics chain satisfies a very weak decay of correlation, then its continuous time chain up to time t can be simulated faithfully within OT plus log n rounds in parallel. We are going to explain what is a very weak decay of correlation next. The divergence influence matrix for Glauber dynamics on graph G and specified by mu is defined as follows. For any two vertices U and V, that rho UV takes the maximum total variation distance between mu tau V and mu tau prime V over all pairs of neighborhood configurations tau and tau prime, where tau and tau prime differs only at node U. A series of well-known conditions for mixing is defined on the divergence influence matrix rho. It usually requires some norm of rho is less than 1. For example, the divergence Schultzmann's condition asks the infinity norm of rho is less than 1, implies the contraction of path coupling and O(n) log n mixing time for any Glauber dynamics. In this work, we give some much weaker condition for parallel simulation. Our main theorem requires rho satisfies exists some p that the p norm of rho is a constant. Our algorithm works within OT plus log n depths and polynomial processors in CRCW prime model, and works in OT plus log n rounds in congest model on network G. Since the divergence Schultzmann's condition can imply the continuous time chain mixing O log n time, combining our result for any Glauber dynamics, if the infinity norm of rho is less than 1, the approximate sampling is in RNC class, if ensuring the local distribution of single dynamics is RNC computable. Our algorithm has applications for obtaining RNC samplers. The following results follow from recent results for optimal mixing. Our algorithm produces an approximate sample in O log n rounds for matching, easily and hardcore model, if satisfying the uniqueness condition. To the best of our knowledge, this is the first RNC algorithm for sampling from graphic models with unbounded maximum degree up to the critical threshold. Our algorithm also produces a uniform satisfying assignment for KD-CNF formulas in polylog n rounds if satisfying the local lemma condition. With non-adaptive simulated annealing, these RNC samplers can be transformed routinely to RNC algorithms for approximate counting. Before introduce our algorithm, we first give a process which is equivalent to simulating the continuous time Glauber dynamics chain as follows. First, we simulate a Poisson clock for each node, generate the update schedule. We use Vi denote the ith update at node V. For each update Vi, generate a seed uniformly from interval 0, 1. Let sigma 0 be the initial configuration. Initially, let us sigma get sigma 0. Then we resolve each update chronologically. Take tau be the current local configuration at V. Then we draw with color according to a subroutine sample. Here, mu tau V is the marginal distribution on V. RVI is the random seed of update Vi. Sample mu r is a deterministic subroutine. It returns a spin distributed as a mu by using random seed r for any distribution over Q. In previous process, the configuration sigma changes at each update time TVI. We discretize these moments. let YVI denote the result of update VI. Then the previous process can be stated in a discrete version. For each update VI, we take tau be the configuration of with neighbors. At time TVI, resolve YVI according to tau. Formally, for update VI, tau be the with neighbors configuration at time TVI is constructed as follows. For each with neighbor U, let UJU be the latest update at U before time TVI. Set U's color by YUJU. Now, we introduce our main algorithm. It is an iterative algorithm which can faithfully simulate the previous process. We use XLVI denotes the result of update VI in round L. XL denotes the results of all updates in round L. Initially, in round 0, set result of all updates at node V be the initial color of V. In subsequent rounds, when I is equal to 0, it denotes the initial color at V. Then do the following repeatedly. In round L, for each update VI, take tau be the configuration of with neighbors at time TVI in round L minus 1. Resolve XLVI according to tau. Whenever in round L, the result of XL is the same as XL minus 1. The loop ends and output XL. The algorithm is a message passing algorithm, which falls into a same general framework of the famous belief propagation. In one round, the results of all updates can be computed in parallel. In our algorithm, each update VI depends on some other updates. The dependency naturally defines a directed graph. The directed graph is acyclic, since sort all updates VI by their time naturally forms a topological order. If we fix the update schedule and all the random seeds, use XL denotes the fixed point of main algorithm. YVI denotes the result of update VI in previous chronological simulation. Then for each update VI, the result in XL and Y is equal. It can be proved inductively through the topological order of the dependency graph. Now, we can conclude that the output of our main algorithm is exactly the same as the previous chronological process, which faithfully simulates continuous time Glauber dynamics. In the main algorithm, all the results in round L is computed according to the results in round L minus 1. For resolving update VI in round L, the main algorithm said take tau as with neighbors configuration at time TVI in round L minus 1. Formally, tau is constructed as follows. For each with neighbor U, let UJU be the latest update at U before time TVI. Set U's color by results of UJU in round L minus 1. Note that for each update VI, it uses the same random seed RVI in different rounds. Now, we analyze the efficiency of our algorithm. We focus on the number of rounds the algorithm takes to reach its fixed point. At round t plus 1, we consider the probability the loop doesn't end. It implies exists an update VI. The result in round t and t plus 1 is not same. Let E denote such event. Take the randomness of the random seed of update VI. The probability of E is determined by the total version distance between two marginal distributions and the subrouting sample. We want the probability of E to be small. It can be ensured by following properties. First, if the boundary condition is similar, the marginal distribution are close to each other. This is bounded by influence matrix rho in some extent. Second, if the marginal distribution are close, the subroutine sample is likely to return a same color. In the next, we will discuss how to construct the subroutine sample to hold this property. Let omega be a finite space for two distributions mu over omega. We call gamma a coupling on mu and nu if gamma is a distribution over omega times omega. Take random xy distributed as gamma. Then, for any x in omega, the probability capital S equal to x is mu x. For any y in omega, the probability capital Y equal to y is nu y. By the well-known coupling lemma, given finite space omega and the two distributions mu and nu, it exists a coupling gamma on mu and nu. It holds that take a random xy distributed as gamma, the probability x not equal to y is equal to the total variation distance between mu and nu. If mu and nu is given first, we can easily construct a coupling F on mu and nu, and this inequality takes equal sign. But the challenge is that in our algorithm, the subroutine sample need to be constructed before given mu and nu. This allows us to propose a new concept, universal coupling. Let omega be a finite space, we call F a universal coupling on space omega. If for any distributions P over omega, FPR is identically distributed as P for R uniformly chosen from interval 0, 1. For example, let omega be a space of 3 spins. The following picture shows a coupling F on 3 distributions, mu1, mu2, and mu3. For any real number R from interval 0, 1, F mu1 R, F mu2 R, F mu3 R respectively defines a color in omega. Takes R from interval 0, 1 uniformly at random. Then F mu1 R, F mu2 R, and F mu3 R is identically distributed as mu1, mu2, and mu3 respectively. For any two distributions, takes a same R in interval 0, 1 uniformly at random. Consider the probability F returns different color. We call a coupling coupling performance on two distributions is good if such probability is close to the total variation distance between them. In the example in the picture, the coupling performance on mu1 and mu2 is good, while the coupling performance on mu2 and mu3 is bad. Instead of coupling the 3 distributions, a universal coupling needs to couple all the distributions over omega. Our goal is to construct such a universal coupling that for every pair of distributions over omega, the coupling performance on them is as good as possible. The competitive ratio of universal coupling is defined as follows. A universal coupling F on omega is said to be alpha competitive if for any mu and nu over q, for R chosen uniformly at random, the probability F mu R and F nu R returns different colors is bounded by alpha times the total variation distance between mu and nu. Then we introduce the universal coupling lemma. For any finite space omega, it exists a two competitive universal coupling F on omega. We prove the lemma by construction. We construct our universal coupling F as follows. The random seed R can be taken as an infinity sequence of pairs xi, yi, where each xi, yi is generated from omega times the interval 0, 1 uniformly at independently and random. Our function f takes a distribution p and a random seed r as input, output a sample in omega. F works as follows. Take the smallest I such that yi less than pxi, output xi. The procedure f can be described as follows. We continuously sample a node xi, yi uniformly from the rectangular area. Whenever the node falls into the shaded area, output the x-coordinate of node and it terminates. Since the shaded area is 1 and the total area is the size of omega, we have the following curves. First, in one example, the probability the node falls into the shaded area is 1 over the size of omega. It implies that f requires the size of omega pairs of x, y to terminate on average. Second, conditioning on x, y falls into the shaded area. The distribution of x is identically distributed as p. It promises the correctness of our universal coupling. Now we analyze our universal coupling's performance. For any two distributions, p and q on omega, use the same random bits r. Run the procedure f. Let I1, I2 be the smallest i's, such that yi less than pxi and yi less than qxi respectively. Then the following holds. The probability I1 is equal to I2 is equal to the area of p intersection q over p union q. Here p denotes the red shaded area and q denotes the blue one. The equation can be understood as sample a node xy, conditioning on it falls into p union q. The probability it falls into p intersection q is this. The probability is exactly the Jacquard similarity. We proved our construction achieves the optimal in worst cases. Since FPR and FQR output xi1 and xi2 respectively, if I1 is equal to I2, the two procedures absolutely return the same color. Then the probability FPR and FQR returns different colors is bounded by 2 times the total variation distance between P and Q. Now we conclude that our construction F is a two-competitive universal coupling. Let's go back to analysis the fast convergence. Let a sample be an alpha-competitive universal coupling on Q. Rho is the influence matrix. Take over all the randomness. The probability our main algorithm doesn't end in L rounds is bounded by this formula. Note that in this formula, the competitive ratio of sample alpha to be a constant is the key to ensuring convergence. Combining the universal coupling lemma, we can take alpha equal to 2. It induces if any Glauber dynamics satisfying some norm of rho is a constant, our algorithm terminates in OT plus log n rounds with high probability. In summary, in this work, we give the parallel algorithm faithfully simulates continuous time single-site dynamics up to time t. For single-site dynamics under a weak condition, our algorithm terminates in OT plus log n rounds with high probability. A key step in our parallel simulation algorithm is a so-called universal coupling procedure, which tries to couple all distributions over the same sample space. The universal coupling and its applications are of independent interests. There are two major open problems. The first is there an RNC algorithm for approximate sampling matchings in general graphs? The second is there an NC algorithm for approximate counting in graphs? Thank you for listening.